Okay, so yeah, we're presenting on the randomized testing of the actual Dafny compiler itself. So how do you actually test a compiler? So to do this, well, ideally you'd have unit tests covering absolutely every line of the compiler. However, things will still happen. Even with testing completely done, there'll still be a way to find bugs. So what you do is you generate a test program, you compile it, and you collect its output. In Dafny's case, this could be introducing a main function and actually having it run. And then by some method, you verify the output of it. And if you detect a bug, you reduce the program down, try to minimize it, either report it and leave someone else to fix it, or try and look into a fix yourself. If you don't find a bug, well then you come back and you generate a new program and try again.
Now, the main problem with doing compiler testing is that it's very difficult generally to identify whether or not the compiler is doing the right thing, and this is known as the test oracle problem. So for unit tests, it's very easy to encode an oracle, the expected output, because you kind of manually program that into a unit test, whereas with a randomly generated program, it's much more difficult. So there are two ways to solve this, the first of which is called differential testing, where you, instead of just running over one compiler, you would take your generated program and you would run it over a number of different compilers, and then the idea is then that you should see ideally the same result across all of them, or if one of them is different or more than one of them is different, then you might have found a bug in one or more of the compilers. Or there's also something called metamorphic testing, which is instead of running over different compilers, you will now take that randomly generated program and mutate it in some way such that its output should be equivalent. For example, you might have an expression x equals a plus b, you could mutate that to b plus a, and then you would compile and execute all these mutated programs, and then again, if more than one of them is different, one or more of them is different, you should have again maybe found a bug in one of the implementations. So we applied these techniques to Dafny. We will first generate a program. We do something called reconditioning the program to make sure that the program stays valid and it will compile and run without errors. We then pass it through Dafny to each of the backends and perform differential testing over the outputs to check whether or not any one of the backends has an error in it.
So what have we actually done here? We've created two different tools, fuzz-d and DafnyFuzz, which both generate complex programs which are guaranteed to be valid. We then run these programs and actually test it to try and identify bugs in the programs, and as a bit of evaluation, we've evaluated its effectiveness against XDsmith, which was an existing compiler fuzzer for Dafny, as well as the regression test suite for that. When looking at it, we looked at the number of bugs we identified. In particular, we had a focus on the soundness bugs, so where Dafny would produce for example, valid verification saying the program's correct, but the compiler would actually produce something different. We also looked at the line and branch coverage, as well as took a look into mutation testing.
Okay, so for program generation, we took something known as a generative approach, and this means we would recursively walk over the Dafny grammar. We would start with a main function in both of the tools, and then we would select over the constructs of the language. For example, maybe a statement could be an assignment or a function call or something, and then we would use these to then generate the rest of the program randomly. And these would be done using weightings to make sure that we limit the program size to something that can be compiled in a reasonable amount of time.
So in terms of language features, we both look to cover the basic types, so this might be arrays, tuples, basic integers, bit vectors, as well as some of the collection types, so the sequences and sets. But we also took into looking at more complex types, so inductive data types, generic data types, as well as object-oriented types, such as classes. In particular, we also focused on features of the Dafny language that we may have found to be slightly unusual compared to most other languages. So, for example, match statements and expressions, the loops that existed and a small bit on their verification, parallel assignments, and as mentioned, we took a look into some verification features such as pre- and post conditions, invariants, and assertions.
In terms of testing, we ran differential testing, as mentioned, where we would run a program over its different backends and compare the outputs. we'd also do metamorphic testing with DafnyFuzz, where it would produce a number of different equivalent programs and test these outputs. And the benefit of this is then that you can just test one particular backend, for example, maybe the Java backend or the C# backend. You can just generate a number of equivalent programs and test one particular backend. We also looked into mutation testing, which mutation testing essentially analyzes the ability of a test suite, or in our case, generated tests, to respond to real-life changes in the code base. So you would mutate the actual code base in some way, so the Daphne code base, and then we would detect the ability of the test suite, so our tests or the Daphne regression test suite, to detect this particular mutation.
In addition, we also looked at expected output testing, so an ability to track what the program should generate. So when we are both generating the programs, we had some sort of value tracking implemented, so then we can actually produce what we expect the output to be. The advantage of this is now we have an oracle that is completely separate from the actual Daphne compiler itself. For example, making sure that regardless of what Daphne's mutations it does, we know what it should have. We also, as mentioned, took a look into verifier testing. However, this was not our focus. It turned out that it was something a lot more complex in randomly generated programs, and in terms of actually having a precondition that was, or any sort of assertion that was actually accurate, was quite hard to do.
So overall testing, which we did in a number of different campaigns throughout the generation of our tools, and also once we'd finished them, we ran a number of campaigns for which we identified 24 unique issues in Daphne, 9 of which were related to soundness, although only 5 of those were classified as soundness, and there's 4 yet to be classified on GitHub. And 9 of the bugs we identified have been fixed. Do you want to go through the different breakdowns?
Yeah, so along with this as well, in terms of languages-wise, we found the majority to do with Java. That doesn't say that it's 8 unique issues, because we saw a range of compiler issues with Java. However, we've estimated down to about 8 unique causes within there. As well as that, the next most we found was in the Python backend, and we found a few with C# and JavaScript and Go.
And in terms of our actual testing, I know we've just put a huge number of numbers in front of you. What we performed 2 main types of testing: coverage testing for the average line coverage of tests generated by our tools, and also mutation testing for the number of mutants using a tool called Striker. And this would be testing a number of different test suites to check how many mutants could be killed or identified by the tools. So for coverage testing, we found that our tools are generally quite a way off the regression test suite, but compared to XDsmith, which we kind of considered as a baseline, we have made significant progress, particularly with fuzz-d, where I believe it was the object-oriented features covered, made quite a lot of progress over XDsmith.
In terms of mutation testing, we saw that fuzz-d performed significantly better than both DafnyFuzz, the XDsmith, and the compiler Daphne regression test suite. However, one important thing to note is that the XDsmith here had only 10 tests timed out and none survived. We haven't looked into this too carefully, but there were 2 issues that we saw with XDsmith. Firstly, in order to get these results, we actually had to increase the timeout settings on Striker in order to get them. And secondly, it might be a case that some of these timed out tests were killed by the other testing tools. But it appears at this point that while both fuzz-d and DafnyFuzz perform better than the regression test suite.
Okay, so we'll now talk through a few of the different bugs we found. Bear with me while I try and do this. So the first of the bugs is an example of what can happen at runtime, in particular with regards to type safety. So in this case, we found a multiset, which is essentially a set where you record the cardinality of the elements as well. And we've created a multiset where we tried to set the element 1 to have a cardinality of 2 to the 32 or 2 to the 64. And we found that for both Python and C#, this would result in an overflow exception. And this was evidently a bug because Daphne's integer implementation is meant to be theoretically unbounded. and this was handled correctly in the other backends. So it was clearly just a missing point in the implementation of the other backends. So we'll go on to, I think, this one.
Yeah, so this was a bug actually found during the process of generating both of the tools. What happened was, under the right conditions where you had match statements as well as parallel assignments, what would happen is the actual Dafny compiler would crash. While this seems like something that could be normally just a standard bug report, this was actually introduced as part of another fix that went in. So this was only discovered after we upgraded our Dafny version from what we were working on locally. Luckily, at the time, we were reporting quite a few issues, and the team reacted quite quickly and managed to solve the issue, and we managed to continue testing.
Yeah, and it's a good example of how continuous random testing can show, can identify regressions in compilers. So this one was, again, just a slightly different example. We were testing slightly more complex features, more unique to Dafny, and we found that certain combinations of the language, so for example, if you do a for all statement inside some pattern matching, then you would end up with some more invalid code generations for the particular backend, so in this case JavaScript and Python. So we see here clearly they're trying to reference this 2A, which has been generated by Dafny, where it's not been defined yet, and I think that's been fixed. Sorry, this is really difficult to... Okay.
Yeah, the last one we'll look at is a Go miscompilation issue, and this is where you have an unreachable bit of code, but for the Go language, the way continues and breaks were implemented was by jumping to a label, whereas in this case it would actually cause the Go output produced to crash. So if you keep scrolling down, see here, it jumps over a declaration. Again, helpfully fixed, and was able to continue testing these statements. Do you want to give your demo?
Yeah, we have a little bit of time, so we'll use what's left to give a demo. I'll just get up the IntelliJ. Yeah, that should be big enough. Okay, it's huge. So how our tool works is we'll invoke it using just the fuzz, the name, and I'll get a seed so we can do some seeded generation to make sure that we get the right outputs. Sorry, there's a lag on the display, so I'm having to work from a lag. So if I provide this seed, it will produce a program in output here, which looks something like this when it generates. Okay. Yeah, so this is roughly what our programs will look like. You'll see we start by generating a number of inductive data types. Then we have this global state, which will essentially act as some global values which we carry around the program, as they can help identify more issues as throughout. So instead of losing data at the end of a scope, you can now use this global state to carry on data beyond the particular scope. Then we go through some function methods, which are just mathematical functions, and if we scroll down about 500 lines, you'll see we get to the body of the program, which has a number of different statements and so on. And then when we run it, we'll find a number of issues. For example, this is using quite an old version of Dafny now, so it's crashed on the Java backend and emitted a number of warnings and exceptions. So this is an example where we found potentially a number of bugs in the Java backend, whereas all the other backends have emitted a particular output successfully, and there was no other issues there. So we'll now go back to the presentation. Okay.
Yep, and we'd just like to conclude at that. Thank you, and we're happy to answer any questions.
Hi, thank you for the talk. I just wanted to ask, you mentioned two tools that you implemented, fuzz-d and DafnyFuzz, I think. Can you explain the difference between those two?
They would just happen to be implemented at the same time. We were both working on the same project, and it meant that there was some small differences in the approach we took. So, for example, fuzz-d mainly looked at the differentiating between the different outputs on the back ends, whereas DafnyFuzz looked at metamorphic programs, so they generate equal outputs.
Yeah.
There was also some small differences in features that they actually look at and implemented.
Okay, great. Thank you very much.